Hi, hello, welcome back to the stream today. This is my little nerdy space on the internet where you'll find talks about technology, you'll find deep thoughts, and you'll find curly hair. I am a resident scientist and technologist, Aleia. For those who don't know me, I am a budding engineer and inventor. Right now, I'm studying data science as a student at Make School. I'm a senior there. I also have Instagram, Facebook following as well. I'll put those links in the comments, but you can find that at Robot Gal. And I also have a Medium blog where I talk about personal development, career development, and technology as well. And like I said, I'll put the links to those below as we go through. But today on the show, I'm going to be talking about fractals. And so what we're going to do in a typical fashion is we'll talk a little bit about what fractals are, explain them, give some examples of like real world examples of what they are, and then we'll get into a little bit of code. We'll make some of our own fractals. I'll give an example of like 2 or 3 that I've coded. And then from there, we'll give us like a little conclusion about what we've done and wrap things up from there. So just to get started, I'm going to share my screen with you all. And to start off, I'm going to show you a article that I wrote a little while ago. I'll go ahead and drop the link to that right now in the chat for anybody who wants to pull that up on their own, who wants to look at it more in depth in their free time. So this is an article on fractals and recursion. And this got brought about because I was learning about recursion, and that's really what the heart of fractals is recursion. Recursion is the idea of something happening over and over and over. It's kind of like that saying that insanity is doing the same thing over and over and expecting a different result. Well, that's kind of in a way what recursion is. You do something over and over and over, and you're not per se getting a different result, but you're slightly altering the result that you get until you get to a certain point. You're like, okay, we're done here. And in the world of coding, that can lead to a lot of errors where you start reaching infinity. You could break your computer because you just keep going and going onwards. So you need a lot of processing power for things like that, and which is why we come up with things called edge cases to get us out of those situations. So I'll talk about that a little bit here. Okay, and yeah, so when we talk about recursion, something over and over, we'll go here with definition of what it is. And what that leads to is fractals. Like I said, it's doing the same thing over and over in a loop. And so here's some quick tech difficulties or that. Not too cool. So when we get into these fractals, um, we want to take a moment and think about what different examples of fractals we see in the real world. One of the most common ones that people think of is snowflakes because they stretch out infinitely and they're all different. And the difference with like snowflakes or different fractals is that no two ones are going to be exactly alike. And that is part of the beauty of fractals is it's the butterflies. Why are we? So I'm gonna pull up pictures of ones that I think are the best. So here's a couple examples. The binoculars here. And I'll just show that off for a second. We also have the circular infinity. And you see one of the telltale signs of fractals is it goes from something very large to very small. So in this case, you have this very big image, but as you zoom in and you see closer and closer onto that image, that the same image is repeating within itself. And that is one of the key features of fractals. We call it self-similarity. It's when you see something and it's repeated within itself, similar to recursion. So I'll take a moment, pull that back, look at another one. So you see there's still these giant circles, but then there are smaller ones there, and it's the exact same shape, but they're getting smaller and they're still filling in all of these spaces. A very similar concept that is brought up in regard to this is the concept of fractal dimensions. I'm sure everyone who's here has heard of something called the multiverse theory or the multi-world theory. But there's also another one, and it's the fractal theory. And what that is the concept of affinity 1, 2, 3, 4, 5, 6, onwards to infinity. You can keep adding numbers and it's never going to stop. But when you think of this concept of fractal infinity, you can get 1 and 2 points. And if you break it in half to halfway, then it's still, nothing has changed, but there's still tons of possibilities in between there because you can continuously break that number in half. Always. You can always get a smaller number, and that's just between 1 and 2. So you can imagine between 2 and 3, 3 and 4, with the infinite number of whole numbers, how many infinite number of fractal numbers that you have. And that's where you get really cool pictures like this, it's called the reverse Julius set, where no matter how small you go, it keeps going. And so that kind of sums up a little bit of what fractals are. And so what we're going to do is I'm going to pull up a tool. It's called processing. You can just pull that up. It's a free download. Let me see if I can pull up. I can pull up. I'll share the link. Natively, processing is in JavaScript, but you can add, there are libraries that you can add that allow you to code it in other languages. Fractions and fractals, they have similar names, but they're not like built off each other. They're related in the sense that fractals are broken down into pieces. You have a whole and it breaks down and it reflects itself as it keeps going down. Whereas fractions are similar in that sense that where it's a piece of something else. But I think it's more so fractions can help explain fractals. And we'll see that when I switch to the first fractal that we're going to build. Is called the Cantor set, which is actually this one here. We're going to build that out, and you can see just looking at it that we're breaking it into like thirds as it continues to go down. And so it's not that they're the same, but they do kind of reflect each other. So I put the link for processing down there, and as well that if you go to the article, and I'll put my GitHub on there as well. But all of the things that I'm coding on here today, as well as everything that is coded in the article, is going to be found on my GitHub at github.com/robotgal. So you can pull it up there, and that way you can use it as a basis to go further into it yourself. So I'm going to open up processing, and it just starts off with a basic sketch. Like I said, there's this drop down here. You can use p5.js, which is a very common one. It's the native one on here. A lot of people also choose to do JavaScript, Java or JavaScript. And I have it set on Python because that's the most familiar language that I work with as a data scientist. It takes off a lot of the extra steps that you may need, and it just can get you straight to the point of coding and visualizing exactly what you're looking for. So I'm going to do that. So what I'm going to do, rather than coding everything 100% from scratch, because it is all here written out, I'm going to pull it up and load it so you can first off see what pops up and how it loads things. And I'll go with you step by step in the code and explain how we got to what we got to. So, and we've got to pull up. So if anyone has ever done Arduino, which is it's like a small circuit. It is a microprocessor, often used in robotics. And processing is a way it ties in the sense that they are, their development environments are very the same, and the way that they run their code is very the same. So you'll have this output down here, which for us and our purposes, we won't really be using it too much because we want to see things visually rather than just numbers popping out on the screen. We can do that too. We can do that too, but let's see if I can make that bigger. I'm just gonna see if I can make this bigger. I'm not sure if I can just zoom in. One moment. I'm not sure if I can make this any bigger. No. Yeah. There we go. Ooh, much bigger. Let's just scoot that up. All right. I think that should be good. And then I'll just keep that in mind for the future to make sure we can have that nice and large where you want to see. So yes, what we're gonna do, just gonna run this right now, see what pops up. And then we'll go through and then explain the different functions that are running in here and how we can edit certain things as well. So if we run this, we get this simple output here, just like what we had in the article. And to break it down before we get into the code, you see that we have the one main line. We're going top to bottom, one line. And then when we get to the next line, we say, okay, we want two of that line, break it out. We want a space in the middle. So of course we have like a little visual room. But we're printing out that same line, just smaller down. And for each one of those smaller lines, we say, do that again. Give us two more lines broken into a third piece with a space in the middle. When you do that on that next smaller line, do the same thing again. And we want to keep repeating that down and down. We can do this infinitely, contiguously, of course. our human eyes can only see but so far, which is why we stop after a certain point. Oh, but this is a very basic idea of what a fractal is, and it's similar to the idea I mentioned earlier of you can get a number and you can continuously break it in half. You can just keep breaking it in half without any end point. So exit out of there. So to go through this code, every time in processing, you have to have a setup function. This is to give you like a canvas. So if I have a picking it, so when you create this setup function, what you're going to is going to, as is called setup, it is your setup. You have to have one in every single processing code that you write. Otherwise, nothing's going to run. It'll say, yes, we see other things there, but like, how do we get started? And so initially I had the 500 values here. But if I had changed these, say, to 800 instead and ran it, we get a bigger screen. So that's really what the size is in the setup. Is saying how big of a screen do I want my code to print out on? Because we're not doing anything too crazy or just doing some lines, I just set it at 500. And that way we have a little bit of a smaller screen that we can see. Okay. And the next setup is, this is our initial line. This is our function, and we're going to run this in the beginning in our setup. As soon as we start, we're going to say, look at this function, and we're going to make this function, of course, later down here. But this is really the main function that's going. So we say run the function, and these are our inputs, 10, 20, and the length that we're looking for. So to explain what we're doing, we make a function called cantor, and these defines are just how we identify functions in Python. So you don't have to too much worry about that. Of course, different languages will have different ways of setting up your functions, but for Python, it's just define. And so we see we have a cantor, we have x, y, and a length, and these are just going to identify to us how we're going to draw the line. So inside of there, we say the stroke weight is 3. Stroke weight is a function of processing. So if you go to processing.org, there is a reference sheet in there, and it very clearly breaks down everything you need to know about how to do that, about the built-in functionality of a lot of the things that happen here. So stroke weight is exactly what it sounds like. 3, if I say, let's pick 8, since that seems to be the number today. Run this and get like very thick lines, very bold lines is what that does. So 3D seems very well. Let's just stick with that. Now, the important thing about recursion and fractals, like I said before, is they can go on for infinity. If you don't have something to stop them, then they will continue to go on to infinity. So this one we set up these if statements here so that we can keep going. I don't stop this one because it's so small, but we'll see in the next one that we do that we'll have exit conditions. And what an exit condition basically is say we, in the case of dividing by half, if I had 100 as my starting number, I say, okay, we're breaking it in half. Now we're at 50. Break it in half again. We're at 25. Break it in half again. We're at 12.5. Keep breaking things in half. And to a point where I say, okay, I've seen what I needed to see. I need you to stop. Otherwise, we're just going to keep going until like super, super small infinity numbers. So I can tell it if the number gets to 1, then stop doing what you're doing. And that's how you exit out. Otherwise, you get things like in code, they're called runtime errors or stack overflows, where It just, your computer says that you're going too far, you're doing too much, you're exceeding the bounds of what I'm capable of doing. Uh, that is because the reason the bars looks the same in this is just because of the zooming that I have. If I zoomed in, I didn't build a function in this particular one to zoom in. We'll see that when I code or when I pull up the Mandelbrot set, to where you can click on it so we can visually see how it changes as we get closer in. But on this one, because it was just a simple introductory one, there's no zoom in function, and so the lines look the same. So yes. So the function is, if the length is greater than or equal to 1, then we're going to draw a line. Simple enough. And once again, this line function is a built-in property or built-in function of processing, and it just says what is your x value, what is your y value, where it's telling where we're starting the line, where we're stopping the line. So it's just like a coordinate system. If, for example, I was drawing a line on like a coordinate plane, I may say, I want you to start at point 0, 1, and I want you to go all the way till point 2, 1. And that would draw us a vertical line, just straight up like this. So that's the same concept of this line function. The 0 and 1 will go here, and 2, 1 will go here. So it knows where to draw the line. You can do diagonal lines, up and down, side to side. If you want to do shapes, there's other functions for that, because this is basic. You change, of course, the stroke weight with the stroke weight up here, but since we don't need to do it every single time, we just do write it one time in the beginning. Then we say y plus equals 20. That's saying that, let me pull this back up. So it's just going row by row down this. In processing, Arduino, and many other Canvas-based code visualizers, y positive, going higher in number, and the y is actually moving down your screen rather than up your screen. It's kind of counterintuitive because when you learn about the coordinate system in middle school, I guess, or maybe elementary school, y usually goes up. And that makes sense when you think about the real world. Usually, the higher you go, the more up you're going. But when you think of canvases in the code world, keep in mind that the more positive your y gets, the further down it's going. So yeah, it's kind of like reading a book where the further you go, the more down you go in the book. Left to right and down, at least in the American reading system. Um, so we're incrementing by 20. So just order that value. Chase. All right, and then we function again twice. The reason we call it twice is because we want 2 more lines every time. If we wanted 3 more lines, we would call it 3 times. And that is really the root of recursion, as well as the root of fractals, is calling a function inside of itself. That's where you get those like almost inception type things where it's like, I'm in a dream, but there's a dream and a dream inside a dream. Inception is a movie about recursion and fractals. And if you watch that movie, after watching the stream, you'll notice a lot of trends in there that look, a lot of visuals in there that look very fractal like, very broken. And that's really where the origin of the word fractal comes from, is from the Italian word fractia, I believe, which means broken, because it looks very broken. You're breaking it down into smaller pieces. So these two, we're saying we want 2 more lines. The first of those 2 lines, put it at the position we're looking for, but we break the length into 3. And we're breaking that length into 3 because if you look at it, technically this line, this first one, is only a third of the original because we want that even space in the middle and we need space still for the last line. So we're breaking it to a third. Similarly, on the last one, you see we're also breaking it into a third piece, but we moved this location. We moved it the length of the original line times 2/3, and that scoots it like way over here. If we just did break it in a third and keep it at XY, it would be right on top of our first line. We wouldn't see it. We would think it's an error when it's actually there, just in the wrong location. So we scoot it all the way over to the end. And then what it'll do, because we have this Cantor function or setup, it's just going to keep going. That is the thing about the setup function in processing, is it keeps iterating over and over automatically unless you tell it to stop. So by doing so, once we draw those 2 lines here, it's going to go right back up again. And they say, okay, now we're back here, draw those lines all over again. And it's just going to keep drawing over and over. So that's really the simplest form of a fractal that I probably visually pull up. Let's see, we have 30 minutes. So I'm also, before we go into the next one, well, I'm not going to exit out of there. Before moving into the next, I'm going to share another resource with you all. And this is probably where I spent the most time learning about fractals, and a lot of where I really kind of fell in love with a lot of the visuals of them. It is called paulbork.net. I'll put that into the chat. Cool. And Paul Bork is a researcher who looks into fractals, more on the mathematical side of things and trying to solve for their equations. But going through their page, you start to get these images down here. And these are all sorts of fractals that he's found, other scientists have found, like this fractal space filling one that I pulled up earlier, the Lorenz attractor, which is one of my favorites. And I do have that one. I will pull it up as well real quick. I'm not gonna go too in depth into the next 2 just because they require such a high level of math. You have to go into like derivatives and partial derivatives and calculus and break things down like that. But I will run it to show you. So a couple things with this one. For one, you can see very small in the bottom, some numbers going, and those numbers are just pointing out the coordinates and the number of iterations through. Nothing that we need for our purposes, but if you wanted to map it to figure out a formula, then these numbers will come quite in handy. And then over here, the original plan was to be able to move it around in a 3D space so you can see it because it's an actual 3D image, whereas the one we just did, the Cantor, was purely 2D, just lines, just lines. This one is actually a 3D image in a 3D space, but because I was not able to code it to move around, it currently looks 2D. But you can kind of tell it's 3D with the way that it's moving around as well. And so we have it moving in a 3D space, and it's just going to keep going. It's going to iteratively go closer to those 2 points in this, but it's never going to get truly to the center. And that is what's called an attractor. It's trying to pull it inwards, but because of the way that the formula is set up, it's also going to move back out and then back in and back out. So let me exit out of there. And this page was very useful because it talked a lot about where it came from, and it also gave the formulas. And some of these fractals you might be able to spend hours of time trying to figure out, but these resources like these really come in handy because the formulas are given for you. Now, of course, you have to do a lot of work yourself to try to figure out how to turn those formulas into code that the computer can understand and then actual visualize, which is why when we pull up the formulas, we have them written out, and they're the same formulas, but we had to create different variable names. We have so we have all our constants here. We made new, we had to write out our formulas, constant names as well. And some of these are given values. So you'll, once again, as I stated before, with fractals, if you change just the slightest number, it can like supremely alter what different pictures and visuals you get out of it. And so you see down here, when people do it, there's like other researchers and scientists, they may use these as the constant numbers that they put into their values to get the pictures they get. And I could put those same values in myself and get a different image or the same image that scientist researcher got. But I wanted to try it out a little. So here are different like examples that people have used. So you can see, and it's all the same formula. It's just different constants that were put in to get different results, different coloring, all sorts of things like that. So this is do I have any thoughts about that triangle? I had that one pulled up. I believe you're referring to this triangle. I mean, it's also fractal as well. I haven't been able to code this. I don't think it would be too complex to code. It's similar to the Cantor set in the ideal that you would start with one piece and you would break it down by thirds as you continue to go through it. It just would be a matter of the shape of it. And they're always even illustrated in this type of way where you're constantly zooming in. I like this one because I'm a big nerd and it reminds me of the Triforce. But otherwise, like I mentioned, when you're back here, there are so many different ones to go through. Some are easier to code than others. My so one of this one here, the binocular, is my favorites. I have a bunch. It just looks really cool. I personally have like when I look at the formula up here, I was like, this is just mind blowing. And I wouldn't even know where to begin coding it. But it's one of those challenge things, and it's one of those really cool things to look at because fractals are natural occurring things as well. You know, in nature there is no true straight line. And even in chaos, there's beauty. Even leaves, I think I have it in the article that's way down here, below the Mandelbrot set that I'll pull up, is what's called Barnsley's fern. And this is just a fractal. It's just like many others where you put in the formula and you can alter certain things in different colors, but ultimately you get this here, this fern. And it's just a good representation of nature because you could even go outside right now. You can pull a leaf off a tree and look at it, and you can see how the branches are trees. I have here a tree that I animated, and it's a fractal. where you can see is one branch and it breaks off into two other branches. And each of those two branches breaks off into two other branches. So it's very like fractals, I think, are a good way of like using math and science and technology um, to replicate nature. These are things that we see naturally in nature, and even I'll show the Mandelbrot set in a moment, but the Mandelbrot set was found by accident as a mathematician was looking for patterns, and they started noticing patterns in their data. And because of technology, it was until like years and years and years later that we had the technology to code up the images. Um, and now we're able to put those formulas in that before were just theorized and actually see the results of that. Yes, so like I said, fractals have been around for centuries. Difficulties. So, yeah, fractals have been around for centuries of time. It's a concept that has been studied. And like I said, before really the idea of fractals came about, it really stemmed from the idea of recursion, of mathematicians, really more so mathematicians and scientists, uh, looking and wondering about the concept of infinity. And the more you looked into the concept of infinity and trying to quantify what it is and find ways to, formalize it or to very distinctly quantify what infinity is, that leads you into those concepts of recursion. And I think fractals was a a byproduct of that. I think it was a mix. And of course, I'm sure there's plenty of research out there. I myself haven't read all of the information to give exact details, but from what I've read and what I've seen, I think it was a mix of um, one, we did get to a point where we can start to look at these things more visually. So I think that brought recursion into this idea of fractals and fractalization, as well as using looking at nature and wanting to be able to understand nature. And I think it's really looking at the sky and wanting to understand space and black holes and stars, looking at in grass and nature and trying to understand even the human body. If you look at like the eye, at the way the blood is, looking at these type of things and trying to understand their patterns and how it works. A lot of that does come from the idea of recursion and how far can you push something, how big can you make something, how small can you make something. And I think it just, with the development of technology, especially computer science, being able to have the processing power to really look at these things, uh, it really started becoming bigger because we can visualize those numbers. Whereas, back in the day, they didn't have those things. They may have to write every single iteration out. Yeah, yeah. Um, yeah, so we write every single iteration by hand. And now, later with the advancements of computer science, you're able to have the computer power to put those numbers in and see what comes out of them. So lastly, I will pull up my favorite, or one, not my favorite, but probably the most known fractal that I'm sure everyone has seen. Cool. Yes, so I'm gonna pull this one up real quick. And while I'm pulling this up, because this one does take a little more time and processing power, I do invite you all to like look into fractals. Just quick Google search fractals or fractal images or cool fractals, or even just go to, like I said, the Paul Bork site, and take a moment and look through these really cool. I think the first time I did this, I spent like 3 hours just looking at them. And feel free to share your favorites like in the chat, or, like I said, I'll put as well in the chat and share just like, I don't think I have a sticky note. I can put on a sticky note. My sticky notes want to open today because they didn't want to open last week for some reason. I think they're going to open up. I'll write it in here while I pull that up. But you can always send these to me as well. That is my Instagram. My Facebook is also the same at Robot Gal, or you can just look at the article here. Okay. And so, like I said, this is my Instagram. But I invite you all to go ahead and take a moment while I get this situated and share some of your favorite ones in the chat. Or you can send them to favorites. Like I said, mine is the binoculars currently, but every time I find a new one, it always changes. So I'm gonna pull this up, and I'm not gonna go while you're doing that. I'm gonna go ahead and talk just a little bit about the Mandelbrot sets, just because it's very in depth. If you go back to the Paul Bork site, it does have the formula there. The reason I could go too in depth about this one is, like I said, this one requires a very high level of math. It requires much linear algebra, mostly just calculus. You have to do derivatives and some partial derivatives. Of course, feel free to read through my article or go to any of the links that I provided, and of all our variables. This draw function is telling us what we're going to do every time we want to draw this. So this one's going to run a bit differently because it has to load the image. So there's a lot of math in here, and we're not going to go too into it. I think there's 4 main formulas, and each has like baby steps in that formula because of the derivatives. And then I have a color set here. So my red, green, and blue, and I have them based off of other variables so that they can change into a full spectrum based off their location, as well as a mouse press function so we can zoom in and look. And that I'll pull it up so we can see exactly what that does. But that's so we can click on it, zoom into the picture, and see results of that. That is cool. Thank you for sharing that resource with me, Ignat, on YouTube. And this takes a little bit to load up. I'll put it right on top. So yes, here's these. You just click and it zooms in. So as we'll zoom in, see how they get closer and closer. And I think just me myself, I've always really been into like arts and maths and sciences, and I am a firm believer, which is why I say I'm an engineer and I'm an inventor, but I'm not like a computer engineer or a mechanical engineer, because I have very strong beliefs that they all kind of blend together. And that's really why I like fractals, is I feel like it's a really cool way to blend math and science and art together. I think I really got interested in it like when I was young. I don't remember exact. I don't think it was like an exact moment. Um, there's like coloring books. I think that's what it was. Is there were coloring books that just had like art in them. They were just like weird shapes and snowflakes and just like repeating patterns like flowers and just cool designs in them. And I think that might be, as a child, the first time I really saw fractals. I didn't really know what they were, but just looking at them and being like, oh, it's the same shape over and over. And I can like color them, green this and then orange and red. And like it just keeps, each one was different, but I knew there was like a something to them. Like I knew it wasn't just like, a picture of like a landscape or a picture of just a rose to color. Like these things that I was coloring weren't just everyday items. Like they had a certain pattern. And being so nerdy, I love patterns. So looking at them, I was like, there's some sort of pattern here. I don't know what it is, but I'll figure it out one day. And I think that was probably like my first introduction to fractals, even if I didn't understand at the time what they were. And then as I got older and took more math classes and started seeing like how things repeated and finding other patterns and going to computer science, learning about recursion, it just all kind of started like blending together and falling into place. So that's really what got me down this path of fractals. And even to this day, there's all sorts of things I want to create with them, like find other fractals. Because the thing about them, the beauty of fractals, other than just their actual beauty, is that they are just here. They just naturally occur in the world, and they've always been here. You know, they're not new things. They've always been here. It's not like we magically hit the 21st century and like they just out of nowhere. They've always been here. We just haven't had the technology to see them, and so it makes you wonder about what other cool fractals are out there we haven't discovered, or what else we can see as we continue to like if I were to keep clicking and keep going, I'm not kind of concerned it's going to break my computer. Um, it's just if we had stronger computers, more processing power, or just better technology, what other things could we find? Um, and that really leads, even further into that idea, or the growing field of quantum research. These things have always been here. And if you just keep getting smaller and smaller, finding these power sources or these other things that just already existed that we're discovering can be utilized and have always been here, and that we can, really bring to the forefront if we have a passion and an eye to look out for them. So while I was ranting about the joys of fractals, I've just been clicking around this and showing like just different patterns, and you see, the swirling shape repeating in on itself. If I reset it, run it again, we'll go back to the original fractal. But then if I were to start clicking in another space, it would give a completely different set of images. And that was the idea of fractals, like I said before, is one initial change in the beginning can completely alter the results that you get at the end. If I were to do them like way, I think it's here, I think, and it should give me almost the same Mandelbrot. If I clicked where I think I clicked, yes. So you see that on the Mandelbrot line, there are like smaller exact Mandelbrots there. Um, as a side note, if I haven't mentioned, Mandelbrot is named after the scientist Mandelbrot, or the mathematician Mandelbrot, who actually discovered the formula for this. Um, he wasn't able to see it come to fruition in the way that it has. But this concept of self-similarity is really powerful, and it's really leading into a lot of cool technologies, like I said, and the ideas in the realm of quantum research and even space research, because like the ideas of fractals, of course, we're getting smaller and smaller as we click onto these images. But um, but like I said, we in this example, we're zooming in, so we're getting smaller and smaller. But it also applies to like space research as well. We're constantly get bigger, and that's where we get the idea of like the observable universe, where we understand the idea that you can always double something. You can always add one to something bigger. And that's when you go out in the space and you find these really cool things out there. Like one of my favorites is the pillars of creation. And it's like these gas clouds in space, and these different galaxies that exist. And nebulas. Mm-hmm. Cool, cool. So we get all these different galaxies, different iterations, and it brings that idea of like no two things are exactly alike. Um, and it circles us back to the idea of the butterfly effect, where maybe not in the exact same terms of the original concept of if the butterfly flaps its wings, storms happen on other planets. But it is the same concept of by tweaking one thing or changing your initial starting point, or one color, or if I were to click at one point here versus if I clicked at one point here, it gives you completely different things. And it's really it's really mind blowing, to be honest. It's very, very mind blowing when you look at concepts like these. So um I don't want to get too much more in depth about fractals, because I could really sit here all day and just like go through fractals all day, but I do want to be respectful of everyone's time. So once again, I do want to thank everyone for coming here. Um, Again, here are the links to my Instagram and my Medium. I also have a Facebook page you can follow. It's Aleia Knight or Robot Gal, has both on there, and you'll find like me putting up more information about space, about technology, about math and science, about once again like personal development, how to like really get into things like this. And so feel free to follow me there, reach out to me, share these fractals with me. Um, that'll wrap up our show for today. But I will want to leave you on the fact of, for one, next week we'll be having another show, hopefully with less technical difficulty. And we're going to be doing snowmen. So we're going to be using processing again, I'm pretty sure, or a very similar technology. And we're going to be building snowmen. And so what we're going to do is I'll share with everyone, maybe some intro code, and we'll live stream building different snowmen, different shapes, get in the holiday season, have a little fun. And for this one, you want to do a call to action where we want you to code along with us and, you know, make your own version of a snowman. Have a little fun with it, do a little colors, do a different shape, even if you wish. We're coding, we can make whatever we want. And we ask for you to send in your pictures to us, to the Make School Instagram, I believe. We'll be sharing more details about this very soon to the Discord. It should be in the chat, I believe. Yes, so I'll put that again. I'll put it on the chat once more. So it's make.sly/join Discord. This is our Discord channel. And if you submit those to us, then we'll go through them. We'll share people's images as well as do a competition. And whoever wins the competition will send you some swag, some special results of that. So we'll be sending out more details about that coming up, but that will be our show for next week. Maybe building snowman and code. And so thank you again for joining us. I will just, as a quick reminder, this week we usually do have tech topicals with Brian Ross after me, but we will not be doing it this week. However, he will be back next week on his tech topicals to share some information about technology and the world and the future. So thank you again, and I hope you all enjoyed it. I will see you all next week.